Here in section 4.5, we're going to be looking at how well we can predict the graphs of higher order polynomial functions. And we're going to use a lot of stuff that we already know combined with a few new ideas. And we're going to see that in a general sense, we can actually predict the shapes of these graphs pretty well. There's certain things that we don't have quite enough math yet to do completely accurately, but a great deal you will be able to predict. Here's sort of a general strategy to introduce where we're going. Right? We'll rely primarily on four important elements of these graphs. First of all, the X-Intercepts. We already know that if we can find the zeros of the function, basically we know the X-Intercepts, right? Because it's where y equals 0. So to find the X-Intercepts, we just solve f of x equals 0, or in other words, find the zeros of the function. We just spent a whole section in 4.4 talking about how to do that. When we're lucky, we can factor. When we're not quite so lucky, we may have to use the rational zeros theorem, but hopefully we can get to the point where we can find the zeros of our function. The y-intercept, we already know how to find that, right? For the y-intercept, we just sub in x equals 0. Or in other words, find f of 0. The end behavior. We've talked about end behavior a few times this semester already, and we can predict it for certain types of functions, right? We know how to predict end behavior for quadratics. We know how to predict it for power functions like x cubed, x to the fourth, x to the fifth, and so on. We're going to talk more generally about how to predict end behavior for our polynomial functions. And then the last important thing that we'll need to kind of use to define our graph will be the turning points, that is the maximums and minimums. This we'll learn that we can often, although not always, predict that they exist in their general location, but this we're still going to usually need to rely on technology to find specific locations. It actually turns out that we need calculus to predict the exact locations of the maximum and minimum points. So I hope when, not if, but hopefully when you take some higher level math, you'll get that last piece in place. But for our purpose, we'll still rely on technology to do this. Okay. So ultimately, our goal is to use our equation to predict as much of this as we possibly can, and then apply it to what the graph looks like. Doing mathematics like this, using an equation to find a graph or understanding the relationships between a graph and an equation, is called analytic geometry. It's kind of a little branch of math that we're dabbling in right now. All right, so we're going to start talking about graphing functions, polynomial functions, that are given in factored form. So for each of my functions, I'd like to work by hand to determine the zeros and the y-intercept. Then we'll use technology to complete our graph. So here I have the factored form, and the zeros would just be what I just simply get when I set my function equal to 0. I'm going to write this out very formally this first time, but we'll probably take a few shortcuts as we go along. This really means that x minus 6 equals 0, x minus 1 equals 0, or x plus 1 equals 0, which gives me x equals 6, x equals 1, and x equals negative 1. I'm hoping that you're kind of to the point where you could say, hey, I don't really need to write out that middle step. I probably could go right from here to there. And in fact, I will be starting to do that. Those are technically my zeros. If I wanted to make them into x-intercepts, I would just make them points with y values of 0. All right, the y-intercept. That's just plugging in x equals 0 or finding f of 0. So if I do that, I would have 0 minus 6, 0 minus 1, and 0 plus 1, which is going to give me positive 6. So 0, 6 is my y-intercept. I'm going to put all of that information onto my graph by hand, and then I'm going to be using Desmos to help me from there. So let's see, our x-intercepts were at -1, +1, and +6. The y-intercept was 0, 6, and it says we have to put a scale. So you know what, maybe before I actually plot my y-intercept, I probably should use Desmos because I don't know how big I'm going to need to make the values on the y-axis until I kind of see that. So let's go ahead and get some help here. My function was x minus 6 times x minus 1 times x plus 1. All right, and I'm clearly, the bottom is kind of cut off here, so I am going to adjust this just a little bit. There, that works. By the way, notice you can see what we already knew. There's those x-intercepts, -1, 1, and 6. And there's the y-intercept there at 0, 6. Looks like I have a minimum here at approximately a little bit more than 4, -30. And I need to make sure that my graph reflects that. I can see down at least that far. So let's see here. I'm just going to go ahead and make each one of these 5s, just like my graph did. So this would be 10, 20, 30, and so on, and -10, -20, -30, and so on. When it says you must give a scale on the y-axis, I'm expecting you to do exactly that. Write in your scale so that I can tell what you're counting by on your y-axis. So my 0, 6 then would end up right about here for my y-intercept. And then we said just a little more than 4, -30, so roughly here was our minimum. And I'm just going to sketch it in from there. Oops, I missed that by a little bit, get the idea. All right, so that's what my graph would look like. All right, the degree. Go back over here for just a second. Without bothering to multiply all this out, which we definitely don't want to do, I can see it would be x times x times x, or x cubed. So this is going to be a 3rd degree. Okay. We already said the zeros were x equals 6, x equals 1, and x equals -1. And the x-intercepts, list those as well. We already found the y-intercept, it was 0, 6. All right, let's talk about the rest of these. What does the end behavior of this graph look like? Well, if you look at it, it's going down on the left side, and it's going up on the right side. So I'm just going to say down to the left and up to the right. The turning points, the maximum and minimum. Let me go back over here and actually get them from Desmos. Looks like the max might be slightly to the left of, yeah, there it is. The maximum, so local max, at about negative 0.08, comma 6.04. And there's a local minimum at about 4.08, comma negative 30.04. Okay. I'm actually going to label those values on my graph because they're going to be helpful to me when I answer the next couple of questions. So before I go back to my paper, I'm just labeling those points just like they're labeled here in Desmos. All right, so my picture now looks like this. I've got the max and the min labeled. And I've also written them in the table here. All right, I'm next asked for the intervals of increase. Here's where having the max and the min labeled is really going to help me for the intervals of increase and decrease. So if I kind of think about my graph here, I am, just for my own use, going to label this point here for the maxes. What was that, negative 0.08. And here where the min is 4.08. And I just like to kind of think of this from left to right because it helps me concentrate on what I'm doing rather than going back and forth. So this graph is increasing at first. And it's going to increase for all of the x values until I get to the maximum, right? So the increase happens from negative infinity until I get to negative 0.08. All right. I then have a section of the graph that's decreasing, and it decreases until I get to the minimum, so it decreases in here. From negative 0.08, oops, I went a little bit too far, sorry about that. Until I get to positive 4.08. I have that decrease in the graph. All right, at the end the graph is increasing again, and that starts here at 4.08 and continues on forever. So from 4.08 to infinity, my graph is increasing. And just a reminder, I know we've talked about this before, but it's the hardest thing about the intervals of increase and decrease. They are x values that I'm giving you here, right? Not y values. All right, domain. Our domain has still not gotten any more interesting. The domain is still going to be all real numbers from negative infinity to infinity. This graph goes left forever and right forever. So my domain is still going to be negative infinity to infinity. And that's actually going to be true for all polynomials. My range, this particular graph does go down forever and up forever. So again, from negative infinity to infinity. So we have kind of a complete analysis of this graph. All right, we're going to do another one or two this way and just start kind of getting used to our functions. So in B, if I once again am supposed to find the zeros and then also the y-intercept by hand, to get the zeros, I'm just going to set my function equal to 0. which means that x plus 3 is 0, or 2x plus 1 is 0, or x minus 2 is 0, or x minus 5 is 0. And that gives me x equals negative 3, x equals negative 1 divided by 2, x equals 2, and x equals 5. Those are my zeros. I guess there's a place in the next page to put the x-intercepts, so I won't take the time to write them out now. The y-intercept. I plug in 0 for x, or in other words, find f of 0. So 0 plus 3, 2 times 0 plus 1, 0 minus 2 times 0 minus 5, which is 3 times 1 times negative 2 times negative 5 is positive 30. So 0, 30 is going to be my y-intercept. I'm going to put the x-intercepts on my graph right now. Again, I'll hold off on the y until I find out what kind of scale I'm going to use. But negative 3, negative 1/2, 2, and 5. Sorry, there they are. Negative 3, negative 1/2, 2, and 5 are my x-intercepts. My zeros, really, but I know how to turn those into x-intercepts. So let's write down what we know so far. I would have multiplied x by itself 4 times. So this is going to be an x to the 4th, or degree 4. The zeros are listed right here. And it doesn't take much to turn those into the x-intercepts. Just put those y equals 0s in there. Y-intercept was 0, 30. All right, to do the rest of this, we're going to go ahead and get the graph first, and then we should be able to answer the rest of these questions. So I'm going to go over to Desmos and put in my original function. There it is. And we definitely need to do some adjusting here. Let's see. All right, there we go. So that's a pretty reasonable graph. I haven't cut anything off. I can double check my x-intercepts. There they all are, as expected. My y-intercept, it's all there. All right. I'm just going to go ahead and click on all of my turning points here. And I'm going to try and draw a graph that includes all of those turning points. So it looks like I need my graph to go like at least from, say, negative 50 to positive 100, or negative 50 to 150. Let's do that. So how can I do that? If I count by, not quite enough to go by tens, let's go by 20s. So on my paper, I'm going to go 20, 40, 60, 80, 100, 20, 40, 60, 80, 200, and the same in the negative direction. All right, let's see. There was a, oops, I lost them. I'm going to go ahead and I'm just going to mark all of my maximum and minimum points on my paper as I do this. So let's see, there was a minimum point at negative 2.04, negative 84. So somewhere around here. There is a maximum point at about 0.77, 49.8, so about 0.8, 49.8. Around here. And then there's a minimum at 3.9, negative 126.9. So all I've done is I've marked the approximate location of each of those points on my graph, and I've labeled them. And then I'm just going to sketch in the picture. Trying my best to hit those points that I have already put on the graph. All right, so there it is. The next thing I've been asked about is the end behavior. And I'm going to notice this one goes up to both the left and right. So up to the left and up to the right. The turning points, maximums and minimums, we've got those right on the graph, so I'll just bring them over. There's a local maximum at 0.8, 49.8. And there are two local minimums. One is at negative 2.04, comma negative 84.1. And the other one is at 3.9, negative 126.9. All right, for intervals of increase and decrease, I'm going to go back to my graph for a minute. And again, everything changes at the maximums and minimums, so I'm just going to kind of mark the spots on the x-axis where that happens. This one was at negative 2.04. This one is at 0.8. And this one is at 3.9. And so I'm going to say this function, again, always read from left to right. This is actually decreasing until I hit that negative 2.04. So from negative infinity to negative 2.04, it's decreasing. Then this little section is increasing, right? From left to right, it's going up. And that would be from negative 2.04 to the 0.8. I then have a downhill or decreasing section again, and that goes from the 0.8 to the 3.9. And then finally my graph is going to increase forever after that. So from the 3.9 all the way out to the infinity, we'd have an increasing graph. So kind of going back and forth, I find it easier to just go left to right and label each section as I come to it, as opposed to trying to do all the increases first and then all the decreases. But of course, that's up to you, what works best for you. All right, the domain, again, all polynomials, our domain is going to be negative infinity to infinity. And then the range on this one is a little bit more interesting. Let's go back to our graph. Clearly this goes up to positive infinity, but there's a lowest point on this graph, right? The y values never go lower than negative 126.9. So I'm going to say my range goes from a low value of negative 126.9 up to positive infinity. All right, so we had two graphs that we've looked at, and you could look at more, but these are a little bit time consuming, so we're going to stop right there. What I'd like to try to do is to draw some conclusions about end behavior based on what we've just seen. So if you remember our first graph, the end behavior was down to the left and up to the right. Its degree was 3. Does that maybe bring a few bells? Do you remember what the degree 3 power function looks like? All odd degreed power functions kind of look like that. And notice that the end behavior of our graph, down to the left and up to the right, actually matches the end behavior of the x cubed graph. So our conclusion, or at least our current theory, is that perhaps the degree helps us figure out the end behavior. And in fact, that's actually the case. Take a look at the other one that we did. Okay. This one was degree 4. And if you think about the degree 4 power function, even powered functions are sort of parabola-like, right? And their end behavior is up on both ends, which was exactly the conclusion that we drew here, up to the left and up to the right. So in fact, so far, and I'm going to tell you that that's not a coincidence, that actually continues to happen, the degree, if I think about the power function, actually will help me figure out what that end behavior needs to look like. So based on the graphs that we've seen so far, our conclusions about end behavior. The degree determines the end behavior. In fact, the graph of the polynomial, or the graph of f of x, will have the same end behavior as the graph of x to the n power. And just a reminder, that means for odd ends, we get that kind of a wavy thing where the ends go in opposite directions. And for even ends, we get that sort of parabola-like thing where the ends go in the same direction. Right? So end behavior, very predictable based on degree. All right, next thing we're going to do is we're going to look at a couple examples of graphs that have repeated factors, meaning the multiplicity of the zeros will not always be 1. Okay? We're going to go ahead and identify our zeros with multiplicity. We'll identify our y-intercept. We already know how to do that. And then based on what we just said, we're also going to predict our end behavior, at which point we can use technology to produce our graph. So you will notice if you just look ahead at the next few examples, they're all very similar. They all start with x plus 3 times x minus 1, and then I've just changed the power. This one has an x minus 1 squared. The next one will have an x minus 1 cubed, then a fourth and a fifth power on that x minus 1. So we're going to look at how that changes the graph in each case. So as per directions, we're going to go ahead and start with the zeros. And I am going to start using a shortcut here a little bit. If x plus 3 is 0, x would be negative 3. And if x minus 1 is 0, x would be 1. But because that factor is squared, I would actually get x minus 1 twice. So I'm going to say this has a multiplicity of 2. The y-intercept. If I just plug in x equals 0, I'll get 3 times positive 1 is 3, and my y-intercept is 0, 3. Our new thing to predict by hand is the end behavior. And let's see, we would need to start by saying what the degree is. I have x times x squared. So when I multiply x here times an x squared there, ultimately that's going to have an x cubed in it, and I'm going to get a degree 3. So my end behavior is going to be like y equals x cubed, meaning it's going to be down to the left and up to the right. Okay. And by the way, when I ask you about end behavior on homework or tests or anything, and I ask you to explain it, this is what I'm looking for. So you're going to identify the degree, say that that tells you that the end behavior is like the associated power function, and then describe it to me. That's what I'm expecting to see. All right, I can put a little bit of this in right now. Negative 3 is one of my zeros. 1 is another. I know what my end behavior should look like. Let's go ahead and take a look here. So I have x plus 3 times x minus 1 squared. There we go. I don't need quite such a large y-axis this time. Come on. Goodness, I can't quite get my mouse on what I want. There we go. That's better. All right, there's the 0 at negative 3 and the 0 at 1. And there's my y-intercept at 0, 3. I have a maximum and a minimum here, which I can use to help me get the graph looking a little bit better on my own paper. But what I really want you to notice here is that one of my zeros, specifically the 1, 0, one of my x-intercepts, is also a local minimum. It's a turning point. Keep in mind, that was the 0 that had multiplicity 2. So it seems as though perhaps the multiplicity has something to do with that 0 also being a turning point. We'll keep that in mind and kind of watch for it as we go to our other examples. But for right now, let's get this one. I'm just going ahead and I'm just going to go ahead and say I can count by ones. So 1, 2, 3, 4, 5, and 10, and negative 5 and negative 10. On the y-axis are my scale. I'll put my y-intercept at 0, 3, and then I'll put my maximum at about negative 1.7, 9.5. All right, so this is what I've got so far. I went ahead and put in my y-intercept, and I went ahead and put in that maximum point, and then I'm just going to draw. What I saw here. I'm going to make a specific note that x-intercept at 1, 0 is also a local minimum. All right, and we weren't asked to do anything else. There's no table to fill in, so we're ready to go on. My next graph that I want to draw is quite similar in terms of the function. The only difference is notice that the 0 at x equals 1 here this time is going to have multiplicity 3. All right, as far as the y-intercept, if I plug in x equals 0, I'll have 3 times negative 1 this time, so negative 3. And if I want to predict the end behavior, this would have an x to the first times an x to the third. So there's going to be an x to the fourth in the multiplied out version of this. So my degree is 4. That means my end behavior is going to be like y equals x to the fourth, which I know is the kind of flattened parabola look. And I know it goes up to both the left and the right. So once again, I'm going to go ahead and put in my x-intercepts here, negative 3, positive 1. And probably should hold off on the y-intercept to make sure I can do the scale by ones. I don't know that until I actually graph it. I'm just going to change my exponent here to a 3. Oh, probably a good thing I waited. This looks like it's got a minimum at negative 2, negative 27. There's my 0 at negative 3. And there's my 0 at x equals 1. Notice what happened this time. It's not a turning point. It's not a max or a min. But what it has is that same sort of a little wavy shape that I've seen before when I've graphed some power functions. In fact, look at the exponent on that. Third power, wavy shape. Right? Interesting. Let's go ahead and see if we can get this graphed. I probably better go by, no, even 2s won't do it. I'm going to go by 3s. 3, 6, 9, 12, 15, 18, 24, 9. And I'm going to put in the minimum at negative 2, negative 27. As well as that y-intercept, which we did find by hand, but there it is at 0, negative 3. So here's my by hand graph. I counted by 3s on my x and y axis. There's the y-intercept at 0, negative 3, and there's the minimum, -2, -27. So this came down and hit the minimum, up through the y-intercept, and then it kind of had that little wave in it as it went through my x-intercept. So here's my x-intercept 1, 0, and it kind of has that wave shape. So let's go back just a second. When I had the degree 2 or the multiplicity 2, I ended up with kind of like a vertex. Right? Kind of like you would normally see in a parabola or a parabola-like shape. When I had the third degree, or multiplicity 3, I ended up with that kind of a little wave shape at the x-intercept. So once again, it's not the degree of the overall function, but the degree of the term, or multiplicity of that 0, that seems to be determining the shape at the x-intercept. We're going to quickly look at a couple more. I'm not going to do quite as much detail on these next two. I think we kind of have an idea. So here, our zeros would be at x equal -3 and x equal 1 again, but notice the multiplicity 4. Multiplicity 4 with an even multiplicity, I'm thinking that's going to be another vertex type shape, right? The multiplicity 4 and even is more like a vertex. The y-intercept is going to be 0 plus 3 times 0 minus 1 to the 4th. It's going to give me a positive 3. And the end behavior, I'm thinking this is like an x to the 1st times an x to the 4th. So I'd have a degree 5. Meaning my end behavior should be like y equals x to the 5th. And any odd powered function is that wavy shape. So down to the left, up to the right. All right. I would predict then that this graph is going to go look a whole lot like this first one, right? With the even multiplicity on the 0 at 1, I'm expecting that kind of a vertex shape or a turning point. I'm expecting down to the left, up to the right. I think this new graph will probably be steeper because it's a higher degree, but I think it's going to look a lot like that first graph. Just change this to a 4th power. There it is. Now my vertex is quite a bit higher this time. Here, my maximum rather. But notice there we are at 1, 0. It's got that kind of a flattened vertex shape that we've come to expect from our even powers. The overall degree of the function is odd, but that x minus 1 had an even power on it. I'm going to make a very quick sketch of this. I'm not going to try and get the vertex exactly right. We've seen that enough now. But just for our general idea here, at about -2.2, I'm going to kind of randomly put a maximum on there. -2.2, 83.9. And of course we had our x and y intercepts in the right place. And then I'm just kind of sketching. So I didn't actually bother to make a really nice scale on my y-axis this time. I just simply labeled the vertex so that we can kind of move through these a little bit more quickly. But again, I'm going to notice with a multiplicity of 4, this x-intercept is sort of a vertex or turning point. All right, very last one of these, hopefully again predictable by now. Here we have x plus 3 times x minus 1 to the 5th. So my zeros are x equals negative 3 and x equals positive 1, but with a multiplicity of 5. So I'm thinking odd. I'm thinking that's going to be kind of that wavy shape at x equal 1. My y-intercept, 0 plus 3, 0 minus 1 to the 5th. It's going to give me negative 3. And my end behavior, this would be x to the 1st times x to the 5th, so degree 6. End behavior should be like y equal x to the 6th, and any even-powered function should have up to the left and up to the right. So I am very much expecting that this one is going to look a whole lot like this one, right? Up to the left, up to the right, kind of a little wave with the odd multiplicity of the 0. I think they're going to be very similar. Let's see. Again, other than the fact, of course, that our minimum down here is quite a bit lower, we see again, very similar shape. There are those zeros at negative 3 and 1, and we get that kind of a wave shape going on because of the odd multiplicity of that 0 at 1. So I'm going to more or less sketch this. Again, I'm not going to be super, super picky this time. Missed a little bit of my x-intercept, but we got it. There we go. And my x-intercept here, it's kind of that wave shape. With a multiplicity of 5, odd multiplicity, as compared to the vertex or turning point where we have an even multiplicity. All right, so let's summarize that a little bit, because that's really helpful to know as well if we're going to predict what these graphs look like from scratch in just a few minutes. If we have a 0 of multiplicity greater than 1, what can we say? If we have an even multiplicity, for our 0. Even multiplicities follow the even power functions, and we get kind of that vertex effect, or we get a turning point, we usually call it. At the 0. Sometimes people describe this as the graph sort of bouncing off the x-axis, right? It comes down here and forms a vertex or turning point, or it kind of bounces off the x-axis. when we had the odd multiplicity, for our 0, instead of that turning point or that bounce-off effect, we got kind of a wave shape at the 0. Formally, if you remember back when we were doing the power functions, we called that an inflection point. As the graph goes through or cuts through the x-axis. Those are the ones that look like this. So it doesn't bounce off, it goes through, but we get that kind of a wavy shape. Again, the formal name for that is an inflection point. So the odd versus even multiplicity tells us a lot about what the graph looks like at the x-intercepts. All right, one last question. As we look back at the examples we've done so far, can we say anything about the total number of turning points, the maximum and minimum points for each function? And the hint is, compare the number of turning points to the degree of the function. So looking back, in our first couple of examples, we had degree 3, and there were 2 turning points. In the next one, this would have been degree 4. It's not on this page, but you can see the degree 4. And notice that there's 1, 2, 3 turning points. So in those first couple, it kind of looked like the number of turning points was 1 less than the degree. In fact, that's just going to turn out to be the most we can have. Here again, we had a degree 3, 1 less, 2 turning points. But down here, I have a degree 4 with just 1 turning point. So in fact, the number of turning points, we can't say exactly, but what we can say is it's at most 1 less than the degree. So the number of turning points is at most 1 less than the degree of the function. So if the degree is n, then the number of turning points is less than or equal to n minus 1. Now, in a general sense, we can kind of predict where those turning points are going to happen because we know where the zeros are, right? So when I look back, say at this first one, even though all I knew originally were my zeros, if I knew the end behavior as well, which we now know how to predict, I knew I had to start down, and since I had to go through both of those zeros, I knew in a general sense where that local maximum was going to happen. I didn't have the specific value, but I could tell in general there had to be one around there. So I'm going to say sort of in general, yes, we can predict. All right, so that's a couple of really important pieces that we've gotten in there. I think we probably should start a new video because this has gotten relatively long, and we'll kind of put some of those ideas together.